we talked about how can we handle the homogeneous ODE to solve to have a homogeneous solution. So we use a linear combination of differential operator D to describe a high order ODE. We would like to use the definition of big B to let the high order ODE to become high degree function or polynomial function. So we can use a simple factorization 因式分解 to get the LD. So we could have so we can get the general solution equals to homogeneous solution plus particular solution, and where homogeneous solution would follow dy equals 0, and the particular solution will work for dy equals to and R means the input into the system. And today we would like to introduce more application. Today you better understand what does the R means. So in last week we used some example to learn how to get a homogeneous solution, right? So, for example, in this case, R10 equals to 0, right? So we can get the homogeneous solution easily. It's a lambda 1 and a lambda 2. So you can write down the homogeneous solution with this. And for this, it's a two-cell solution. So you can have an exponential minus x, c1 plus c2x, and a homogeneous like this. B equals to positive or negative I. So the homogeneous will be A cosine x plus B sine x. Right, and then we have some exercise and some practice on different kind of homogeneous high order ODE, right? And in the past we focus on homogeneous solution. I believe all of these are easier. So today we will focus on how to handle the particular solution. And in the textbook, we will learn two basic methods. The first is on determined coefficient method. In Chinese is 代定系数. And the second is variation of variable. The third, we would like to I would like to introduce something we learned in the calculus called differential operator. You help us to solve the high order ODE with more efficient ways. Okay, what does the determine coefficient method means? You can use you can assume the YP equals to the non-homogeneous term, and its derivative, and then plug in the YP into the high order ODE, then you can get the YP. And variation of variable is based on you can have a homogeneous solution, for example C1, Y1, and then you use the homogeneous solution to get the YP. So you use the constant C1 to become a function Y1. Then plug in to the high order ODE, then you can get the YP. So that is the basic idea, but we would like to highlight this. It's more basic, but it's highly efficient and very helpful. So we cannot find this method in this textbook because this textbook is focused on engineering mathematics. So this way would be relative to fundamental calculus. Okay, so in the first two chapters, we would like to make you have a chance to learn calculus and something we learned before. Okay, so before I get into the non-homogeneous high order ODE, I would like to mention some function looks very challenging. It's a one-dimensional, time-dependent Schrödinger equation. So as you can see, it's based on the two variables. It's relative to space. For example, x, y, z, or r theta phi in different coordinate system, or r theta z in angular coordinate, right? It's relative to space, and the other variable is relative to time issue. So this equation is essential to fully understand quantum mechanics and some critical issues in fundamental science or advanced electronics. The reason why do you know some particle called a subatom? Subatom means it's smaller than atom. For example, neutron, proton, exciton, or electron, 中子、质子、电子。